Anyhow, let's continue. Let's talk about some equations up here. If we're talking about an object orbiting the Earth, we're going to assume it's a nice, simple, circular orbit. That way we can talk about centripetal force and centripetal acceleration. So if it's a nice, perfect circle, we can use this equation for the acceleration. Even if it's not a nice, perfect circle, we're going to kind of assume it is. Okay? And we've got this equation, F equals ma. Well, we know for gravitational, that's big G, and this is going to be mass of the Earth, that's the big mass, times the mass of the satellite, whether it's the moon is the satellite, or we're putting a man-made satellite, or the international, like the International Space Station, or communications satellite, or whatever, divided by r squared, equals the mass of the satellite times v squared over r. Okay? Now, depending on what we want to solve for, if we want to solve for the v, that's cool. First of all, what do we see on both sides of the equation? We see an r in the denominator over here, and an r squared in this denominator over here. So we can cancel out this r and this squared. What else do we see on both sides? The mass of the satellite. Right, so we can get rid of that as well. And then we just have to take the square root of both sides, and the velocity is this guy right here. So we can figure out how fast the satellite needs to be going around the Earth at a particular height above the Earth's surface, or more specifically in this case, at a particular distance from the center of the Earth. And we can also see that velocity squared is inversely proportional to radius. Inversely proportional means as one goes up, the other one does what? Goes down. Okay? So increasing the radius means the orbiting object is actually going to be going that much more slowly. Okay, and because of the square business in there, once again, that's a big change. Now, if we think about it in terms of the sun, we know the various planets of the sun. Which one is going around the sun the fastest?
The closest.
The closest one, and the name of that is Mercury. Right, okay. Anyone know why it's called Mercury? Yes? Right. It's named after mythology. Okay. Mercury is Roman mythology. Perhaps you've heard of Hermes. It's kind of the equivalent in Greek mythology. Anyhow, that's the messenger god. Okay, so he was supposed to be able to go around really fast, right? Well, that's why they named this planet Mercury, because it's the one that's traveling the fastest. Okay. Now, once again, we're assuming nice circular orbits. If it's more elliptical, then we'd say, oh, well, the closer it's getting toward the massive object, the faster it's going to be going. And that comes from Kepler's second and third law. Okay, period formula. We're going to use the same basic concept, but a different approach, a different part of the equation. We're still going to use Newton's law of gravitation, and we're still going to use the centripetal force equation, but we're going to use this part instead. So there's the mass. Once again, this is the small mass is the mass of the satellite, and that's on both sides of the equation, so we can cancel that out. Okay, this is the centripetal force equation I had given you a while back. Anything else that we can possibly cancel out?
R.
Okay, you'd say R because there is an R on both sides. However, on the left side, the R is in the numerator. On the right side, the R is in the denominator. So you cannot cancel those out. Unfortunately, there's nothing left to cancel out. So it's not quite as easy, but still certainly possible to rearrange this. You get T. Okay, do you need me to do that on the board?
again.
Okay, all right, sure. Let's see. If we use the centripetal force is equal to gravitational force. Centripetal force, one that we're using this time, is 4 pi squared r divided by t squared, and that is equal to Newton's law of gravity, big G, big mass, little mass, divided by r squared. We can cancel out, oops, I actually forgot to put in the mass in the first place. We can cancel out those little masses, but that's about it. But I can solve for various things. I can solve for r if I'd like. I could solve for m if I'd like. In the previous, in the slide we were just looking at, I had solved for r. Okay, so let's rearrange things and solve for r. What would I do first? I can't cancel anything else out, but I can cross multiply, yes. So I'm going to have 4 pi squared r times r squared is going to be r cubed, okay? And that is equal to big G, big M, times t squared. Now it comes down to what is it that I want to solve for? Do I want to solve for the radius? What would I do if I wanted to solve for the radius? Divide both sides by 4 pi squared and then take the cube root. Right? So I could say r equals the cube root of big G, big M, t squared divided by 4 pi squared. Okay? If I wanted to figure out what the radius was. What about if I wanted to solve for something else? What if I wanted to solve for t? Okay, I go back to this original equation here, and then I'm going to divide through by big G, big M, and take the square root. So I'd have big T is equal to the square root of 4 pi squared r cubed divided by big G, big M. Now, I had already written it on the previous, on the slide. We can say it as T is equal to 2 pi. So I just took the square root of 4 and pi squared. So I'd have r cubed over big G, big M. Okay, that's fine. Is there anything else I could solve for? I could solve, yes, I could solve for pi. I could solve for 4 if I wanted to. Okay, I could solve for the mass as well. What would I divide through by? I'd say mass is equal to what? Here's the mass, so I need to get that all by itself in the numerator. Right, and there's no square roots or anything this time. 4 pi squared r cubed divided by big G t squared. Okay, so if I wanted to figure out the mass of a planet, and it has a satellite going around it, there I go. All I need to do is say, hey, how far away is that satellite from the planet, and how long does it take to go around? This is how we're able to figure out the mass of celestial objects. We figured out the mass of the Earth because we've always, well, as far as we're concerned, we've always had something going around it, right? What is going around the Earth all the time? The moon. If we can figure out how far away the moon is, which is something we've known for thousands of years, and how long it takes the moon to go around the Earth, which is something we've known for thousands of years, we just had to figure out what big G was, and then we had the mass of the Earth. Okay? It's not like you can just put it on a bathroom scale. Likewise with the sun. How could you possibly find the mass of the sun? Well, we've got stuff orbiting it, right? It's us. You plug in that information. Not going to put that on a bathroom scale. It's a bit hot there, right? Oh, just go at night. No, it's not it. Ha ha ha! Yeah, well, whatever. You're not going to respond. I got to get sound effects in here. Anyhow, notice that the object being orbited, that's the important mass. The satellite's mass does not matter. As long as the satellite's mass is small relative to the orbited object's mass, satellite's mass does not matter. So we're not finding the mass of the moon by saying, oh, the moon is this far away and it takes this long to go around the Earth. How would we find the mass of the moon? Well, we'd have to send a satellite to orbit the moon. So we didn't actually know the mass of the moon until, well, I don't know, maybe half a century ago. We sent a satellite around the moon. And we said, oh, okay, the mass of the moon is this. Okay? Hopefully making sense. I think this is a cool application. Find the mass of an object without even making any contact with it. Just having to observe it, and you can figure out the mass of an object.
E stands for Earth.
E stands for Earth. Oh yeah, in this one, yeah, the E stands for Earth in there. As in, this is the orbited object,
Okay.
as opposed to the satellite's mass.
Yeah.
Okay, so remember, the satellite's mass has been canceled out. We don't care about the satellite's mass. It does not affect anything. We only care about the orbited object's mass. So whether we have a big satellite or a small satellite orbiting, same thing. Assuming the satellite's mass is small relative to the orbited object. All right, satellite, think, pair, share.